Okay, today's topic, graphing trigonometric functions. A mouthful. You can see our learning goals are going to be to graph the sine, cosine, and tangent functions and their transformations. So something we've done in the past, meaning the transformations, we'll review those with what they look like with the trig functions. And then also using the graph of the sine function to solve other problems. So characteristics, a lot of that, a different way to look at sine, cosine, tangent today. So let's get started. On this view, you're going to see that I want the sine of theta as my function. But you'll notice I don't have the unit circle. So for those of you that are used to having the unit circle, comfortable with the circle, you could always draw your little sketch of what it looks like, reference point, but still use it. So we are basically taking, think of it this way, and snipping, taking a scissors, cutting, and it doesn't really matter where. We can do it, I suppose, right here at the origin. So we'll take our scissors and we'll cut right there where I made that mark. And then we'll take a piece of it and, like a lasso, flip it out, and we're going to basically have this unit circle be able to be graphed on a coordinate plane. Now obviously if we take, it's not going to turn into a line because we know the values are not all the same, but our point is, what is it going to look like? So first of all, I have down on this one that we should be able to graph this in degrees or radians. All right, so it really doesn't matter. We can do both. Right now, again, our comfort zone is with degrees, so let's assume this is our 90. This is our 180, this is our 270, 360, and then obviously the negative rotations as well. So as your reference point, and you could make these 0 pi, half pi, 1 pi, 3/2 pi. You could do the radians that you learned in the last section as well. So it's not going to change it any. Okay, so we know pi radians is 180, so if you're saying, okay, that's pi, 360 is 2 pi, and as I said, this would be pi over 2 and 3/2 pi. Okay, so if you want to do that, that's fine. We are not doing that. We'll just go with the 90s. We have these in our head, and that should have said 270. So here we go. If we are at 0, question is, remember we're doing the sine, so we're doing the y values. If we are at 0, so I'll place a point at 0, what is the y value at 0? And most of you will say it's 0. So if I'm at 0, my y value is 0. I'll place a point and go to 90. What is the sine at 90? Most people will say 1. And let's assume this was 1 and this was negative 1. So 90 and 1. Then we go, second one. What is the sine at 180? The sine at 180, we're back to 0. What is the sine at 270? Sine at 270 is negative 1. Now it's going to run into my labels here, but we're still good. We'll use them. And then 360, we're back at 0. And it continues. And then again, you could do the rotations in the other direction. So if we go to negative 90, we're at negative 1. If we're at negative 180, we're at 0. If we're at negative 270, we're positive 1. And we're at negative 360, we're back to 0. So if you can now, with a smooth curve, graph what you see, and again, like a smooth curve, now assume, we could put some of these other points on here to help us draw this, but we know what's really happening. It's going up, peaking, coming down, hitting, peaking at a low value, up, hitting, back, peaking at our low value, and we're getting this wave-like result, and I'll do that down here, and it's going to continue in this pattern. So there's a pattern that's established here, and you're saying, well, wait a minute. All the other values are on there? Yeah, all the other values are on there. So we know sine of 30. Let's do some of our exact ones. Sine of 30 equals 1/2. So we're going over to the 30, up, oh yeah, to 1/2. 45, square root of 2 over 2 if you turn that to a decimal. But you've got them all right here. And if you do a smooth curve, you can say, oh, there's some characteristics there. Now that was for sine. We could do the same thing with cosine. We could do the same thing with tangent. That's the whole idea behind this. So from here, taking a look, a little more clean, but still the same graph that I just did, only shows a rotation of 1 full from 0 to 360. And then the cosine, it almost looks like they're attached, but they're not, is 0 to 360 also. But watch, when we had a 0 on our sine, we have 0 on cosine. So watch from key pieces. Here's your 90. 90 was up here. 90's down here. You know? So you're seeing some changes. There it was up there. Right? So they are sort of different waves. Seems to be they're as high as each other, just looking at them next to each other. Seems to be the width of the valley or the peaks are as wide as each other. Now the interesting one is look at the tangent. Look what happens. Here's our tangent values. They're a little different, we know, than the sine and cosine. You have a curve action, but it's a little different types of curve. It sort of just stops, trails off. The closer you get to 1 up here, the closer you get to -1. We are never getting a tangent that equals 1 exactly. Well, we know that's not true because what's the tangent of 45? Tangent of 45 is 1. So you have your 45, which would be, about in here. Right? 45, that's 90, a quarter of that. Yeah. Should be a 1. Oh, that's a 5.0. So we do have a 1 on here. I was reading that as a 0.5. So make sure some of you are not making the same mistake. So this thing gets up there, and it looks like as we get closer and closer, this is the pi over 2, which is 90. 3/2 pi, 270. As we get closer and closer to the y-axis, we have a problem with tangents, it appears. And they become, as you know, undefined at different points. So we do have our 1 listed. Our 1 is right about here when you read it accurately. Let's make it not red though. So here's 90, so half of that would be a 1. Okay, so there's your tangent of 1. And every time you have that 45, you have another 1, wherever you are in your pattern. But it's at the 90, at the 270, we're having this issue. Right here, right in here, down here again, here's 90, okay, -90. So we're having issues of what happens where it approaches, and it looks like we have some asymptotes. Places it appears to approach, but never crosses, never touches. So interesting look at what it really looks like on a linear style graph. Okay. Cosine, as we said, can you look at it and say, what's the domain, what's the range? So you want to be able to do that on all of them. So here I have the cosine and sine, x and y, in order, 2 graphs listed. So if I ask, what's the domain of both of these? And you're looking left to right, you're going to say, well, all real numbers. When you look range, up and down, both of them go from 1 to -1. X-intercepts, when we look at the cosines, we're looking at these points. When we're looking at the sine value, x-intercepts, we're looking at these points. And again, we're in degrees. We could do this in radians as well. But look at it. I think some of us are going to be able to say things like even versus odd. It looks like this is the first 90. 90 times 1, 90 times 2, 90 times 3. That's an odd. This is 90 times 0, 90 times 2, 90 times 4. So evens. Y-intercepts, you're looking at the cosine has a y-intercept up here. and the sine has a y-intercept here. So they're not the same, but they do have characteristics that are similar. They both have x-intercepts. They both have y-intercepts. Domain and range, that's probably a little similar. So these are characteristics we want you to look at, and that's what's listed. So the next couple of slides are just going to be pure notes, not examples here. So domain, as I said, all reals from 1 to -1. The sine wave, the y-intercept was 0. The x-intercepts are the even multiples of 90. The cosine wave, the y-intercept was 1, and the x-intercepts are the odd multiples of 90. Whether you want to remember it visually or you just want to remember from a list, your choice, but we need to remember some of these characteristics. Periodic. If you go back to the graphs, if a graph can be mapped to itself under a horizontal translation, so if it can be shifted left or right, both the sine and the cosine are periodic. They can be shifted, as you look at your pictures, left or right till they match up on top of each other. That's what we're talking about. Functions, if we have the cosine of theta as a function, and g of theta is going to be the sine of theta, they are congruent because each can be mapped to the other with a horizontal translation of 90 degrees. One other characteristic, sine waves are said to be sinusoidal, a new word to use for all you board game players, words, friends, words with friends, etc. Do not forget we've been doing transformations all year. We can do stretches and compressions. And remember, it's that a value out front we're looking for. If there's a multiplier out front of your function, so this would be 5 times the sine of theta, for example, it's a vertical stretch or compression based on that factor of a. Remember, if the multiplier is inside with the sine of theta, it's a horizontal stretch or compression by a factor of 1 over the absolute value of b. So if we say graph down here, y equals 1/2 the cosine of theta, you have to be looking as that's outside of it. So that would be related to the vertical stretch or compression. So if it says 1/2, 1/2 is going to be a compression. Versus the second one, y equals a sine of 2 theta. This is where it's in with the value. So it's in with theta, our unknown, and this would be a horizontal stretch or compression. But based on the size here, we're looking at 1 over 2. So it'll be half a compression, half the size it was originally. So you take the old values and you move them in to half the space. The amplitude of a periodic function is described by half of the max or min value. It'd be good to have a graph here, so let's just show the sine wave here. So when we talk about the amplitude, we're not talking about top to bottom. Okay, we're taking the max value, the min value, and we're taking half of that. Okay, so from a -1 to 1 on our sine wave cosine graphs, we have a value of 2. Take half of that, the amplitude would be 1. So it's basically from this thing, if we cut it in half, the amplitude of one of the waves is 1. Last but not least, translations. Remember, not just moving these up and down and compressing and stretching, but we can move left and right. Recall that when the graph is translated with the function and you have it inside, it's a horizontal translation of the graph, the parent graph, y equals f of x. The translation would be h units to the right. Now remember, it's a minus in the original, so that just has to say, for example, the sine of theta minus 45. If it says that, that's to the right 45 degrees. And if it would have been a plus, then it would have been a to the left movement, a movement to the left. A horizontal translation of sine or cosine is also called a phase shift. So if it gets moved with a value here, then it's a phase shift. And then lastly, the graph of f of x plus k, where it's totally outside of your function. So this would be an example of y equals the sine of theta minus 1.5, like down here. It's outside of the function. It's not included with the unknown variable. It's a vertical translation of your graph from the parent graph, which in this case would have been y equals f of x. The translation is k units up if k is greater than 0, and k units, absolute value of k units down if k is less than 0. So in our example, it's a minus 1.5, so we would be shifting this down 1.5 units. So if our peak used to be at negative 1 and 1, then we now would be down 1.5 units from each of those. Okay, so our low value would now be at, if we are at negative 1, would now be at negative 2.5 as an example. Okay, so we're going to be graphing some of those as well. Those will be a little trickier to do, but we'll do them by hand. A couple other things we're going to do in the book to show you how the phase shift, amplitude are all affected. But I think you have the notes you need for now, so wait till class till we do some of those other activities. Bring some questions you might have, and we should be good to go.